everyone. Just for new people that showed up, this is Shivani Patel with GoEngineer. This is going to be a webinar on a few of the common problems I see inside of simulations throughout all my tech support cases and throughout my classes. As a reminder, all of you guys are muted, so if you have any questions, please just type it out into the messages box in the GoToMeeting, and we'll go ahead and get started. I'm going to be working with a pressure vessel, and this is going to be pretty standard pressure vessel. A couple of things have been cut out of it, and I've already started a couple of the pieces of the simulation here so that we can get into more of the common problems. But to show you guys what I've done already, just a few fixtures at the bottom to hold it together, and some internal pressure on inside the pressure vessel here and inside the manhole. I've also got some global contact throughout the entire assembly, holding all those pieces together. And now I want to try and mesh this to see what happens. And this is the pop-up I get. At first, I see that these two bodies are interfering. Do you want to check interference? So this is the first major issue that we see in simulation and meshing, and it's interference. You absolutely cannot mesh an assembly if there is interference. So jumping into the interference detection tool, I can check my assembly, see that, yes, there are some components that are running into each other, and then I can fix this very quickly. So if you guys have seen editing at the assembly level, that's what I'll be doing here. Jumping into this hole cutout and making it just a little bit larger. To prevent that interference. And I'll exit editing my parts. I'm back at the assembly level. And now let's check that mesh again and see if it works this time. So I'm starting to see some failures, so that's not very good. I get a pop-up telling me what failed. I also have a choice to go into the failure diagnostic tool, but I'm going to do that later. We'll skip that for now. Whenever I see an error like this, the first thing I do is go over to my mesh, right-click and go to Create Mesh, and check out my mesh parameters. So far I've been running the default, but now I'll check into this. Right now I have the standard mesh, the default choice, clicked, with its default middle of the range size picked. So there's two other options that I have here. I have this curvature-based mesh as well. To show you guys what that is all about, I have a little extra piece here. And I'm going to create this first with the standard mesh that we've seen already. So I'll create standard mesh. What the standard mesh does is it creates a triangle size and tries to map it everywhere throughout the entire part, including the circles. So all of these triangles are at the same basic size with a little bit of allowance to change this 0.04. The other type, the curvature-based, has two separate boxes. I have a maximum triangle size and a minimum triangle size. And what that allows is for the triangles to change shape as they go around curves. So this can actually make your curve geometry more accurate, as well as preventing the mesh from failing around really tight corners. I've got two other options here when I switch to curvature-based mesh. This one is the number of elements that have to go around a circle. And this is the ratio of how the small triangles will grow into the larger triangle. Now to see the comparison of these up close, I created a little slide. So I'll switch back to my PowerPoint real quick so you can see this. On the left-hand side, I have my standard mesh. On the right-hand side, my curvature-based mesh. You want to run standard mesh when you're using your larger assemblies or your bigger components, because those triangles will get all the major areas better. You won't be bogged down with tiny little elements in areas that don't matter as much. The downside to that standard is you won't have very good accuracy around curves, and you will potentially have your mesh fail the way it just failed in my pressure vessel. So the first thing I always do if I see that fail, I switch over to curvature based. So let's try that. And I'll also put it all the way up to fine to see if that helps. Now I still did get a few failures. They're a little less than before. It's hard to tell. So this time I'm going to go into the mesh failure diagnostic and see the tools that SOLIDWORKS gives me to fix my mesh. So I have three options here. I'm going to start from the top and go on. The incompatible mesh. This can be great. It can also be terrible. Two different options. When I click this incompatible mesh, it turns on a checkbox in my Create Mesh Property Manager, which will remesh the parts that fail a second time. So as these fail, we'll see the meshing bars complete itself and then restart again to try and remesh those with a different sized mesh. So it did fix some of those. I only have 4 left now compared to the 6 that was before. But before I just continue on from there, I want to actually understand the assumptions that I made when I use that incompatible mesh. And this has a lot to do with understanding the accuracy of what you're doing with the simulation package. So this is another one that I have a little extra piece with. I grabbed one of the manhole nozzles from the pressure vessel. 3 components. I've got the one flange that's sitting flush against this cylinder. And I have the manhole cover that's separated by a tiny gap. Now the compatible mesh that we can do, which is the default, will align the elements so that the stress from one component transitions perfectly into the next component. So I ran a compatible mesh here with the finest level, and if I look closely at where those 2 components connect with each other, I see that all those nodes touch. Now the difference between that and incompatible is incompatible will not force those nodes to be touching to each other. And the way I can force something to be incompatible, I go to my global bonded contact, switch this here in my options, incompatible mesh. And let me remesh this so you can see the difference. And you can see how these nodes do not align with all the other nodes from the flange. So this means when I run this, the stress will not perfectly transfer across. Now the incompatible mesh is necessary for these 2 components that are separate from each other. There's no way to have those nodes connect if there's a gap. So that's the upside to having incompatible mesh. You have to use it when you have non-touching faces. Now I've run 2 studies, one with compatible mesh and one with incompatible mesh, so that you can look at the results. So it's compatible, here's some stress, and at that interface here, I have a nice transition of color, meaning it combined the stress there so the proper transition. But looking at my incompatible results, there's a huge jump in color. This is actually incorrect. This is not how stress would move through the components in real life. And so that's an inaccuracy that can happen without you realizing. So if you are using incompatible mesh in your assembly. Please make sure and that none of the components that are mesh incompatible are touching each other or have bonded contacts between them, because that will be an inaccuracy that you don't want with your result. Let's see the failure again. Jump into my failure diagnostics and do the second option, mesh control. This is the one I highly recommend. And this is the way to increase the fineness of your mesh on different components, different faces. So I clicked mesh control, and what I'll do now is just select the components that failed out of my mesh dialog tree here. So every single one that didn't get meshed completely with the incompatible mesh, I have a chance to redo. I'll put this up to the finest, maybe make it a little bit smaller, let's try 1.35. Create the mesh. It's giving me a pop-up telling me that any areas of the incompatible mesh, it's going to be inaccurate. I understand that. I explained that, so I'll go on. So I have one failure. Let me just add another mesh control for this piece. While that completes, here's a little summary of the compatible and incompatible stuff I talked about here. If you have a compatible mesh, you will get a good transition of stress. If you have an incompatible mesh, you will not. So please don't use incompatible mesh if you have touching parts. So my mesh is completed. I have no more failed parts, so that's fantastic. I can move on to running my analysis. Before I do it, I just want to show you guys the check geometry option very quickly. This is telling us the basics of simulation. You don't want your parts to be too thin so that those elements can go around them. You don't want to have tiny little fillets, otherwise the standard mesh, those triangles, won't be able to go around the curve. This takes me back to where I was before. And this second option here, check geometry, this will help me determine if I have failed faces, failed edges, and this will generally happen if you have imported bodies, imported models. You have some invalid edges and faces, which will break the mesh. But I don't have that. Everything's worked out fine. My mesh has ran, so I'll get into the next most common problem that I usually see, and that is a fixture failure, an unstable model. So as I was running, I get this pop-up. The iterative solver stopped. I've got numerical difficulties. And the only thing they tell me to do is check model for boundary conditions. So my boundary conditions are two things. One is everything in the fixtures. And the second boundary condition is everything under the connections. Now it's hard for me to tell where the issue is looking at this big assembly. Even bigger assemblies, it would be more difficult. So the way we can find our errors, figure out where they are in this huge big assembly, is to turn on this option in our properties called soft springs. You could also use inertial relief in other situations. In this situation, I will use soft springs. What soft springs is a bunch of little tiny springs, kind of like a mattress, and they hold the whole part together all around it. And if it starts to shift a little bit to the left or a little bit to the right, those springs push it back into place. Now they're very tiny springs, so you don't want to be using soft springs if you have a very, very small force or small pressures, small loadings on your assembly. You also don't want to be using soft springs if you'll be pushing your model a far distance. If we all know the spring equation, it's distance times the stiffness. So that's where this is coming in here. The inertial relief option that I'm not going to be showing in the webinar, we can't use it if I have any gravity, centrifugal, or thermal loads. What inertial relief does is balance out the forces in the part. It tries to make the sum of forces 0. So that's how this works. It is very useful if you have a symmetrical part or if you are importing loads from the SOLIDWORKS motion. Jumping back here, I'll be using my soft springs. Click OK and run this. I can see I got past the area that has held me up before. Now I've continued on. I will get this option, excessive displacements, this warning. This is coming up because of that instability in the model that we saw before. It's asking me if I want to turn on large displacements. Earlier I said we don't want to do this if we have soft springs. That's one reason to say no. Another reason to say no, large displacements is more about nonlinear analysis. This is not going to be a major nonlinear analysis, so I will not be using that option. So I clicked no, got to this point, and I can see some of my components have just flown off of my pressure vessel. And those are the ones that still needed some more fixtures or some more bonded contacts. So there are 3 that I need to fix. The one between the head of the pressure vessel and the body, and one between this manhole cover and this one. So jumping back and hiding these results, I'll have to go ahead and fix all of those contact sets. A couple different options. I'll be using component contacts between these components to forcibly keep them together. Choose bonded. And for this one, earlier we noticed how they weren't touching, and that's the reason why they didn't hold together during the analysis. Now I have a couple different ways to keep them together. The proper way would be using bolt connectors. For speed, I'm going to use a contact set and bond them together. So I'll go into bonded, pick one face, pick the other face. And we'll see if this helps my analysis run a bit better. So soft springs was able to help me see where the problem was so I could fix it much faster than some trial and error process. Sorry about that. Looks like my analysis failed there. While it's runs, let me just see if there are some questions going up here. I see someone has said, can you break the meshing tasks for an assembly into both types, standard and curve? The answer to that, unfortunately, is no. You have to do it all one or all the other. So the best way to kind of get around that is to stick with one like standard and then use mesh controls as your second option. Okay, I've got one more bonded contact I need to add here. And that will allow me to finish running this analysis and start looking at those stress results. So soft springs really helped me out, saved me a lot of time. The third thing I wanted to talk about, the third error, has to do with not knowing what these solvers mean and certain accuracies within simulation itself. So I'm going to switch over to FFE Plus because I know this is going to fail. And I'm going to import some temperature results from a different thermal study. But I need to run that first. Let me go over to my thermal. I don't have a complete mesh, so I'm actually going to steal that from my static analysis. Now the way to steal information from earlier studies is very easy. All you have to do is drag and drop from one to the other. So that was able to copy everything over from before. Now let's give this a run, see what my temperature results look like for this pressure vessel. And I ran this with 700 degrees Fahrenheit, so it's pretty hot, and it's very, very low convection. And now what I want to see is how those thermal effects affect the stress in my pressure vessel, so I'll be importing those. So I'll come over to my Flow Thermal Effects tab, import that from my thermal study. And I get this warning this time. It's saying the iterative solver stopped. It's still asking me to check for boundary conditions. But the issue here, which isn't obvious, is that you can't have SFE plus while you're importing temperature results. There's a lot of different inaccuracies like this in simulation. It's hard to tell what's going on. So to help you guys out with that, I've actually created a document that tells you when to use certain solvers so that you aren't sitting here and confusing yourself, trying to rerun different things with your fixtures and boundaries when the actual issue is something else entirely. So to find this document that I'm talking about, you go to GoEngineer.com. We have our Ask Joe search bar. I'm going to type in the solvers for simulation. And the very first option, SOLIDWORKS simulation, choosing a solver. This is a document. And in here I've explained when you guys can use FFE plus, when you can use direct sparse, and so on. To go over it very quickly, auto is a great choice to stick with when you're first starting out with simulation, because what it will do is use this FFE plus, use the iterative solver, until it hits an error, and then it will jump to the direct sparse. FFE plus is iterative, which means doing a lot of guessing. It can be a little bit slower when you're using a lot of bonded contacts, but if you have lots of mesh, it's a really, really high density mesh, it's definitely faster. So please go ahead and take a look at this document when you guys have some spare time. It might help you in choosing your best analysis solver for your study. Automatic. Okay. So knowing that that would fix my issue, the only other thing I wanted to show you guys was other ways to prevent some inaccuracies in your building up the study. Because that's really the hardest thing that we all deal with, knowing whether we have set this up to correctly model real life. So simulation gives us two informational areas to really help us out with this, and they're in the help menu. So if you go to your simulation and go to help, you'll see these verification problems and these benchmarks. So going to my verification problems, I'll see all these little models that you can download directly from SOLIDWORKS. They're already here in your download, and they tell you and explain how to set up certain conditions in certain scenarios. So they can be a great help in showing you the proper way to set something up and without having incorrect assumptions. I was checking out these NAFEMs, these benchmarks over here. These are ones that simulation has to do to be able to be credited. So this is how it proves that it has the correct accuracy for users to be using the software. And if I look at this very first one, this NAFEM linear static, right here I have this asymmetric cylinder under internal pressure, which is great for helping me get started with my own pressure vessel analysis here, telling me what fixtures to use and how to set up my external loads. I'm going to go back and see if I have any other questions, because that's the major stuff I wanted to talk about. Those three major common errors in SOLIDWORKS, dealing with the mesh with all those failures, using soft springs to help you balance out instability. And the third one is that human error, that human inaccuracies, knowing whether to use which solver, and knowing how to use your boundary conditions. So looking at some of the other questions, I have someone from Joe. Joe's got a bent sheet metal part. There's a tiny interference between two of those corners, which will cause the mesh to fail, yes, because of that interference. And is there a way to have the mesh ignore interferences? There is one way. Now, the one way assumes that you're using a shrink fit. I will show you here on this model so you can get a look into it. You are making an assumption that those parts will originally be modeled at the way you've modeled it in SOLIDWORKS, and then you're going to push them apart forcibly. So you're going to have a big displacement stress at that corner that you're talking about, Joe. But show everybody else how to ignore interferences without fixing your model. I'm going to return this back to the way it was before. Get rid of this. There's a contact set called shrink fit. So I come into my contact set choices, go to my drop down, and choose shrink fit here. I have to choose the two faces that are interfering with each other, and that will tell SOLIDWORKS to ignore the interference. Like this, check. Run my mesh. Okay, let me set up this contact set again. Where is it? Click the wrong face. But that's the way you would do it. You click the two faces that are touching that you want to stop the interference for them. And I'll continue doing this for just a minute while I look at the next question. There we go, this is better. So that's how I ignored the interference. Sorry for that little bit of error in the middle there. I hope that answered your question, Joe. For the next question, can you import structural stress data and thermal data into the CFD package? That's the backwards way, actually. You can import pressure data from CFD into our structural studies, but not the other way around. So I go into my properties. I'm importing my thermal data here, and this is where I can import data from flow simulation. But flow simulation doesn't have a way to import the static studies from here. Okay, so that's all the questions that I see for now. Does anyone else have any other questions? If not, I'll just go back over the PowerPoint very quickly. Most common errors that I see, a lot of mesh failures. If you're having a mesh failure, the best order of operation is to try and switch to curvature-based first. If that doesn't work, start using your mesh controls. Mesh control the components that have failed or faces in areas that you want good results in. Avoid incompatible mesh as much as you can, because using incompatible mesh could get you incorrect results, as you can see in these pictures here. If you get a model is unstable error, turn on soft springs. That will help you at least reach a solution, and you'll see the parts that you need to add fixtures for or add bonded contacts for will kind of have flown off the part. So that'll give you a good clue there to edit that. I don't see any other questions. I want to thank you guys for watching. Oh, one more question. So can I go over the advanced fixtures? I have problems understanding some of the advanced fixtures. Yes, I will definitely go over those for you. Let me go into an easier model. This is kind of big and clumsy. So as we get into the advanced fixtures, as we get into fixtures themselves, there's a lot of different choices. They're all categorized by the 3 degrees of translation and the 3 degrees of rotation. If I go into the most simple type, the fixed geometry, this is fixing all 3 degrees of translation and all 3 degrees of rotation. So it keeps something perfectly held in place. When you start getting into advanced, that's how you can start choosing, well, I want this one to rotate, but be frozen in 2 of the other rotational directions. A little bit more freedom to choose those directions. When you get into advanced fixtures, the one that's default selected is the used reference geometry, and this is the one that gets you 3 rotational and 3 translational. You want to pick a face, point, or edge first, so I'll pick one of those. And then you pick something to reference the rest of your directions off of. So if I pick a flat face, then I will have straight edges, left, right, and left and right through the plane and up and down as my choices. But if I choose a round face, I will get rotational directions instead. Now to describe what those all mean, the pictures that can be very, very helpful to you. Look at this very first one. This is expanding the radius in and out. This one's allowing the face to rotate about an axis. and this one expands the cylinder. If I checked one of these options and had this set to 0, this would forcibly prevent this face from being able to move away from the axis, being able to expand. If I set this to something like 5 millimeters, what this does not mean is it can move anywhere between 0 and 5. I'm not saying there's space to move 0 and 5 millimeters. What I'm actually saying is forcibly pull this thing apart 5 millimeters. So I hope that clears up the reference geometry part. That's probably the one that's used most often. The symmetry and circular symmetry options are fairly straightforward. These ones, you want to be clicking a flat face. Circular symmetry, you can click curved faces. Now these both work exactly like a roller slider. The only reason to choose symmetry over a roller slider is if you wanted to look at symmetrical results at the end of your analysis. But they actually work exactly the same. So if you're ever confused between symmetry and circular symmetry, just use roller slider instead. So does that answer your questions about the advanced fixtures there? How about this then? Because it seems like it's still a little bit confusing. There is a tutorial that you can walk through, and it uses one of those advanced fixtures to forcibly push a component apart. So let me go into my tutorials, advanced simulation. And it's this analysis right here, the nonlinear contact analysis of a pipe holder. This one will actually walk you through one of the advanced fixtures, how to use that displacement, pushing one component across a certain distance. That's what those advanced fixtures are really used for. I have another question from Igor. Is there any way to open up a single surfaces model straight from a scanner? So you can scan data directly into SOLIDWORKS. You'll probably have some sort of STL file. The types of files that SOLIDWORKS can open are the STL or the step files, the IGES. You can open those. It'll be a bunch of surfaces. And SOLIDWORKS simulation can run analysis on surfaces. But what you'll be using instead of the solid triangles that we saw here are shell elements. So those are completely flat triangles. So you can do it with surfaces if you wanted to. Someone asked me what version of simulation am I using. This is 2014. I have up to Simulation Premium. So Simulation Premium would get you static all the way into nonlinear and linear dynamic. You have Simulation Professional that gets you thermal through the sub-modeling choices. If your question was just about the year, yes, I am using 2014. If you guys have questions on older versions, I can give you a little bit of an insight into that. If you're looking at what's new for 2015 instead, we're always going to have rollouts in your regions if you wanted to see what's new to 2015. Okay, guys, I don't see any more questions coming in. I hope I was able to answer a few of your questions the way you were looking for, and that you got a little bit of insight into few techniques to make your trial and error process as you're running studies go a little bit faster. If you have any questions, I'll be sending out an email later on. And you can always email me back with any questions or give us a call on our tech support line. We're always happy to help. Thank you guys for watching very much. Have a good day.